Hello once again to our students out there who are watching this video. This is your teacher, Mr. Marvin Earl or Rabino. So for today's discussion, we are going to talk about one of the consequences of plate motion, and that is in the form of earthquake production. Yay! So without further ado, let us now dwell into the world of earthquakes in relation to the plate tectonics theory. In today's video, we are going to talk about the nature of earthquakes. First and foremost, how it is produced, and second is how do the distribution of earthquakes help us understand the formation of plate boundaries and fault lines. And at the same time, we are also going to dwell into this discussion some of the things that geologists do in order to detect earthquakes. Some of the common scales or instruments used to detect or to locate earthquake epicenters. So, I know at the back of your mind you have an idea already. What is an earthquake? Well, it's a very cliche phenomena. We experience earthquakes on a daily basis. It's just that we barely feel some of these earthquakes because of maybe the earthquakes are of little magnitude, so we don't feel them. But in fact, there are hundreds of earthquakes being recorded every day. So that's why it is very important for us to understand this phenomenon because it could affect us. It could endanger our lives. It could also pose significant threat to our um, properties. So that's why understanding earthquakes is essential, especially that we are living in this so-called Pacific Ring of Fire, where most of these earthquakes are frequently happening. So, what is an earthquake, right? That should be the question. What is an earthquake? Well, an earthquake is just, in our layman's term, is the shaking of the surface of the earth. But how does this shaking occur? Well, it's from the sudden release of the Earth's energy. The sudden release of the Earth's energy in the Earth's lithosphere that creates seismic waves. So, as this energy is being released, they travel in a form of vibration, which we literally know as the seismic waves. And these seismic waves travel and radiate on the surface of our crust. And this literally causes the shaking motion of our plates. That's why it's called earthquake or the shaking of the surface of our planet. Now, what causes this shaking? That should be the question. Now, this shaking is mainly caused by the stress experienced by moving plate boundaries. You have to remember plate boundaries where two plates meet. And because it is the interface between two plates and it is constantly in motion, we can therefore somewhat infer that the rocks underneath the plate boundaries experience constant stress as they rub against each other due to its movements, right? So as they move, they experience stress. And as this stress happens for a period of time, energy is being stored and being built up. And once this energy becomes stored, and eventually the stress could not be handled anymore by the rocks, suddenly the rocks will snap and release this energy in a form of vibration. And because of this, faults could be observed, in some areas wherein it is mainly described as the linear zone of weakness, where most of the energies coming from the earthquake are released, or it is the site where build-up of energy is happening. Because as what I've said, in the plate boundaries, rocks experience the greatest stress due to the movement of plate boundaries. So if we could recall, there are a lot of types of faults. First, we have the deep slip fault, wherein it is an inclined fracture where the blocks have mostly shifted vertically, meaning to say there's a vertical shift in the block of rocks. That is what you meant by the deep slip faulting. And there are two types. We have the normal faulting, and then we have the reverse faulting. Now, we can easily identify the difference between these two, because when you say normal fault, it's usually the hanging wall is below the footwall. That's how we identify a normal fault. And this is mainly caused by the tensional stress exerted on the block of rocks. And as a result of this tensional stress, the hanging wall could descend downward and the footwall will go up. That is what a normal faulting is like. In somewhat in contrast, hanging wall and footwall could also be reversed, and that is why another type of fault called reverse faulting happens. Now, reverse faulting happens when there are compressional stress exerted between the block of rocks, and because of this compressional stress, the hanging wall could go above the footwall. Hence, the name reverse faulting. So, remember, normal hanging wall is below the footwall. But if it's a reverse fault, the hanging wall is above the footwall. Now, another type of fault, this is what you call as the strike slip fault, which is usually associated with the transform plate boundary, wherein the rock strata are displaced mainly in a horizontal direction, meaning to say there is a sliding motion parallel to the line of fault. And usually we classify them into two types. We have the left lateral strike slip fault and the right lateral strike slip fault. So it happens only on the interface of the crust, wherein there is a sliding motion in the horizontal manner. So that is what a strike slip fault is all about. And as what I've said, this is mainly associated with a transform plate boundary. There's a similarity between them. In fact, they are the same. No? So, rocks experience stress, as what I've said, near the plate boundaries. Too much stress on rocks may exceed on their elastic limit. That is the ability of materials to bend. Just like a rubber band class, when you are going to stretch it for some distance, there will come a time that the rubber band will reach its elastic limit, and eventually when that happens, it will snap or it will break. And as a result of this breaking process, energy is released in the process. And once this happen, in terms of rocks, they may rupture and release this energy in a form of vibration, which we know as the seismic waves. And these vibrations radiate and travel through the surface. And if you're seeing the map right now, you can see where this energy is released, or the point where this energy is released and rupture occurs. That is what you call as the focus of the earthquake. And directly above the focus is, of course, what you call as the epicenter. So, as with volcanoes, earthquakes are not randomly distributed over the globe. I want you to check the map here. As you can see, these are actual data wherein earthquake epicenters are being plotted globally. And there is a distinct pattern that you can actually observe. Usually, areas that are near the plate boundaries are studded with earthquakes, are studded with earthquakes, just like with volcanoes. So, we can say that volcanoes and earthquakes are somewhat related to each other since they are located near plate boundaries. And what could that be attributed to? It's because at the boundaries between plates, friction causes them to stick together. And when this built up of energy causes them to break, earthquakes then occur. Much as the same with volcanic eruptions, right? Buildup of energy happens mainly at the plate boundaries, and we can observe that especially in convergent plate boundaries, magma deposits are much somewhat abundant because of the subduction that continuously take place in between convergent boundaries. So there is a pattern actually. So we can somewhat deduce that earthquakes are not randomly distributed over the globe. Although they may happen anywhere at any point, there is a distinct pattern. That is, it happens usually near plate boundaries where rock stress are experienced the greatest. And because of this, because we talked about the seismic waves that radiates and travel, which is the main reason why the energy of the earthquakes are being distributed, or the energy of the earthquakes travel outward, we can classify also seismic waves as follows. Body waves, wherein these are the type of waves that travel only through the Earth's interior, and the surface waves, which only travel along the Earth's surface. And surface waves are mostly associated with most of the destruction that happens during an earthquake. So let's further discuss about these seismic waves. I know you're familiar with body waves, P waves and S waves. So P waves or primary waves, they are called compressional waves, meaning to say they oscillate back and forth parallel to the direction of their travel. So as you can see there, we have the compression areas and we have the rarefaction areas or the dilation areas. So I want you to think of a P wave like a slinky, wherein if you bounce it back and forth, it creates also somewhat like a wave pattern, right? So that's how a P wave travel. And P waves travel the fastest among the seismic waves. In fact, P waves are the ones that are first detected in a seismograph, an instrument that is used to detect an earthquake. So that's a P wave. Well, S wave or the secondary waves, they are called as transverse waves because the direction of their particles motion is perpendicular to their motion. So what does it mean? So I would like to somewhat simplify it by just imagining a rope tied on one end of a wall, and then you start jiggling it up and down, and you will see that it will create a wave pattern in the manner, and that is how an S wave travels. So S waves travel next to P waves, and in fact the body waves are the ones that are mainly used in order to detect the location of the earthquake, and we will discuss that one later on. So another one, we have the surface waves. We have the love wave. We're in the direction of the shaking of the surface is back and forth. Okay, there's a back and forth motion of the shaking of the surface. While in Rayleigh wave, it could be described as a rolling motion on the surface. So usually I would like to associate it with when you are riding a boat and the waves start striking your boat, and you will feel like there's somewhat a rolling motion. So that's how a Rayleigh wave feels like, and that's what surface waves are all about. Now, how do we detect earthquakes, or how do scientists or geologists detect earthquakes? Well, an instrument called seismograph is used to detect the vibration, while the seismogram, okay, that's they are different. The seismogram is the paper output that contains the vibration pattern of the seismic waves. So seismograph is the instrument, while seismogram is the vibration pattern that is printed on paper. Now, the method that we usually use is the method called triangulation, wherein you need to measure the arrival time of P waves and S waves in the seismogram, okay, or in the seismograph. Usually, we take the time difference between how long did P wave arrive compared to S waves. Now, the difference in the arrival time of P wave and S waves would help geologists pinpoint how far is the seismograph station from the earthquake's epicenter. So, at least you need three stations for this because, for example, if there's only one station, if I can identify how far my seismograph is from the earthquake's epicenter, well, I could not pinpoint at what direction is the earthquake epicenter. It could be north, it could be south, it could be east, or it could be west. So We need additional two stations so that when we plot them together and create a circle with a radius equivalent to the distance from the earthquake's epicenter, where the three circles meet, that is where the epicenter of the earthquake. So that is why it is called a triangulation method, because you need at least three seismograph stations. Now, there are a couple of ways to measure the earthquake or how strong an earthquake. First, we have the intensity scale, wherein it is the extent of the damage caused by the earthquake. Meaning to say, it talks about the damage brought by the earthquake. And we use the Mercalli modified scale for this. And then for other type of measuring the, shall we say, earthquakes, is the magnitude, wherein it is the amount of energy released by an earthquake at the focus. And we use the Richter magnitude scale for this. So we can easily identify an intensity and magnitude scale by just simply looking at the numbers. Usually, intensity scale is denoted by a Roman numeral, while in the magnitude scale, it's the alphanumeric scale. So just like what you're seeing right now. So this is the Mercalli versus Richter scale. Now, I want to emphasize here that the magnitude scale is a logarithmic scale, meaning to say, at every increase of the magnitude by one level, the intensity, oh, not the intensity, the magnitude of the earthquake gets 10 times stronger. So, for example, if you're going to compare magnitude 1 to magnitude 2, magnitude 2 is 10 times stronger than the magnitude 1, so because it is a logarithmic scale. So, I guess I need to stop from here because I don't want to dwell too much about earthquakes. There are a lot of things to be discussed about earthquakes, but I'll leave the next discussion. So, let's summarize everything here. Earthquakes are primarily caused by the sudden release of energy in the Earth's interior. And this is due to the fact that the rocks underneath the Earth's interior experiences stress. And as this stress becomes too much, rocks exceed its elastic limit and eventually they rupture. And they release this energy in the form of vibrations, which we call as the seismic waves, which radiates in all directions that causes the shaking motion of our plates. And as what I've said and as what I've shared earlier, earthquakes are very much related to plate boundaries. It's because plate boundaries are the site where most of these earthquakes are happening, due to the fact that at plate boundaries, rocks experience the greatest stress. That's all for today, my dear students. I hope that you have learned something from our discussion for this lesson. Thank you very much for listening, and I hope that you continue to learn, continue to aspire, and that you continue to enjoy and learn science. Thank you so much, and God bless you. Goodbye.